So far in dynamics, we've been talking about mainly rectilinear motion, so that's motion in one direction, whether that's your x-axis or your y-axis, or projectile motion, which is kind of a special combination of both. But what if we have something a little bit more complex? What if we have curvilinear motion? So that's motion on really any type of curved path, something that's not perfectly linear, where we have our particle moving from one location to another. We're going to have a couple of different ways that we can approach this, but our general overview of curvilinear motion is that it's still basically using the same concepts that we talked about in rectilinear motion. And that's that idea of relating those position, velocity, and acceleration. But now we're going to be primarily looking at it through a vector lens. So whether we're using rectangular components like our x, y, z, or we might be using normal and tangential components, we might be using polar coordinates, we'll have a few different ways that we can approach these problems, and we'll talk about those in specific videos. But as a general overview, when we're dealing with curvilinear motion, essentially, we're going to be using some kind of reference point and then basing everything around that. So from our reference point, we have a position vector r to somewhere where the particle is on our line over here. A position vector r. So unlike s, where s may be tracing, s is really the position on the curve of this path, the r is just a vector from some reference position, from some fixed point that is not going to be moving. So from a reference, we are going to have our position given as r, right? So from some fixed point to where the particle is, this is going to be our position vector. And that'll usually be in terms of time. So this is our position. And just like we did for rectilinear motion, the relationship between position and velocity still holds true. So we can take the derivative of our position to find velocity. Velocity in a vector form is just going to be, it's going to be dr dt, right? The derivative of that position with respect to time. It's still the same relationship, we're just looking at it through a little bit of a different lens and with a few different qualifiers. And one of these different qualifiers is that velocity is always going to be tangent to the curve. So what that means is anytime we have our particle, let's say our particle is right here moving along this line, our velocity is tangent to that curve. Tangent to that curve, it just touches at one single point in the direction of travel there. Velocity is tangent to the curve, always. Always tangent to the curve. So from some fixed point, we can find our position vector r, and then our velocity is going to be tangent to the curve. But it still maintains that relationship. Derivative position will give us velocity, and likewise, our derivative of velocity is what will give us our acceleration. So these are all the same equations that we had been looking at, the same relationships that we had looked at in rectilinear motion, but really now we may be dealing with 2D or 3D problems instead of just single straight line problems, where it becomes a little more important to be treating these as vectors. So anytime we're doing these curvilinear motion problems, what we're going to want to remember is to put things into vectors, and then we're going to have to choose a coordinate system that works for us, because usually one will work better than another. And we're going to talk about in this video and in the next few videos some approaches you can use to figure out which may be the best approach for you. And it may be problem dependent, right? One problem may be much better to use one system over another. And so in this video, we're going to look at probably the simplest and maybe the one that is most intuitive, and that'll be our rectangular coordinates. So when we're talking about things in rectangular coordinates or rectangular components, what does that really mean? And that's really just going to be our very basic X, Y, Z coordinate system of talking about things. So if we have an X, Y, and maybe a Z, we could just be in an X, Y coordinate system or a Z, Y coordinate system, something in 2D. We could do this in 2D or in 3D. And we have some path of motion that a particle is on. What we're going to have is a description of that velocity, a description of that position, a description of that acceleration. All of those are going to be in our XYZ terms. So looking at this little kind of picture that I've drawn here, if I want to get a position vector, I can come from a reference point, which is often the origin in an XYZ coordinate system, and draw a position vector out to where our particle is, to at any instant in time, where is the location of that particle on the path that it's traveling in this curvilinear motion. So this we're kind of familiar with. We've seen this form of position a lot in statics, right? Where position is some x component, I hat, plus a y component, j hat, plus a z component, k hat. Right, so position we're just describing in these terms of x, y, and z in a vector form. Where we can get the magnitude of this position by taking a square root of the squares. We get the magnitude of r is going to be our x squared plus y squared plus z squared, square root of all of that. And so we can take this and move it down into velocity just as we did in rectilinear, just as we had just talked about in curvilinear by taking a derivative. Right? We said that the derivative of that position is what gives us velocity. And it's very important to note that this derivative of position is with respect to time. So your x and y and z may not be in terms of time, but this is what we're taking the derivative with respect to. You might have y in terms of x, and you might have like an x in terms of time, and you'll have to do some substitution. But this derivative, again, is always in terms of time. So our velocity being the derivative of the position over time is going to give us a Vx component, I hat, plus a Vy component, J hat, plus a Vz component, K hat. And you could see this written in a lot of different ways. We could see this written as Vx, we could see this written as x dot. X dot. So this is a really common one that we may come across in this class or in other classes, is this dot notation, where this dot notation really just means the derivative with respect to time. So it's an x derivative with respect to time. We could also think about it as dx dt or x prime of t. This is another notation. These are really just all different calculus notations, depending on if you're using Newtonian calculus or Leibniz calculus or different notations in calculus, but they all essentially mean the same thing. So you may come across this x dot or this dx dt. It's just important to note that all of those mean the same thing. It's just that derivative of that component with respect to time. So like our Vy would be y dot. And it's just y with a dot on top of it. Simple as that. The same as dy dt. And it's the same as y prime with respect to t, where y has to be a function of time. right? Derivative with respect to time. Vz is our z dot, derivative of z with respect to time, or z prime t, if we have some z component there. So again, notation is always with respect to time, but you may see it in any of these different forms. The dynamics textbook does really like to use this dot notation. I'm not the biggest fan of it, but I will be using it since that's what our text loves to use and heavily relies on, and so I just want to make sure that we're all aware that you could see any of these in any of these different forms. They all mean the same thing. Then when we come down to our acceleration, as we've discussed it before, just the derivative of velocity. So again, acceleration in vector form, derivative of the velocity function with respect to time. So we can see this in many forms. We could see this as ax I hat plus ay j hat plus az k hat. We may see it as ax. You may see it labeled as vx with a dot over it, v dot x, v dot subscript x, I guess. Or you may see it as x with two dots over it, right? Representing that it's the second derivative of that position with respect to x. So that, again, we can see in a lot of different ways. Dvx over dt, could see it as d squared x over dt squared, telling you it's the second derivative of position, x double prime of t, or v prime of t, v sub x prime of t. Any of these, you may see it in this form. So ay is v dot y, or y with the two dots over it. Az is v dot z, or our double dot z. Any of those, totally interchangeable. And much like our position, we can also find the magnitude of these velocities and these accelerations by square rooting the squares, right? So our velocity, the magnitude of the velocity is going to be square root vx squared plus vy squared plus vz squared. Likewise, the magnitude of our acceleration is just square root of all those components squared. Ax squared plus ay squared plus az squared. So again, really helpful if you're given things in terms of x, y, z, those x's, y's, and z's also in terms of time. One more thing that I want to mention with these is that we may find our x and y in terms of each other through taking derivatives. So there are a couple of important calculus reminder rules that I want to point out. And that would be that if we have the derivative of y with respect to time, so dy dt or y dot, that's going to equal dy dx times x dot. And if we think about this in the dt way of writing, where we have dy dt equals dy dx times dx dt, well, here we can find that everything just cancels out, right? Our dx's cancel out, and we end up with dy over dt is dy over dt. But this can be really, really helpful if we're given a y equation in terms of x, where we need to relate these things together. We have velocity in the y direction is the derivative of the y in terms of x function, giving us a velocity in the x direction. So this is something that can be really helpful if we need to get between y and x, if we need to figure something out, some relationship between y and x that we may or may not be given. One more form I want to post of this is that y with 2 dots, right, our double prime of y, is dy squared dx squared, so that's the second derivative of the y function in terms of x, times x dot squared, plus dy dx x double dot, so 2 dots on that x. So this is really helpful for relating velocities with the derivatives of these x and y position with our accelerations. So we can also think about it like ay is the second derivative of y with respect to x times vx squared, plus the derivative of y with respect to x times ax. And so these relationships may also help us move between this velocity, acceleration, and position, as well as going between our x and y. So with that special rule in mind, and with these relationships between these vectors of position, velocity, and acceleration, let's go ahead and take a look at an example of how we actually use all these things. So in this example, we can see we have this weather balloon that has a function that relates its place in space in the x and y directions. So we have at any instant the horizontal position of a weather balloon is defined by x equals 8t feet. So I'm gonna go ahead and just pull that out as a given right now. I know that x equals 8t feet, where t is in seconds. The equation of the path is y equals x squared over 10. Let's make a little note of that. That sounds pretty important. Y is x squared over 10. Determine the magnitude and direction of the balloon's velocity and the acceleration when t equals 2 seconds. So we want to find our velocity at t equals 2, as well as our acceleration at t equals 2. And those are supposed to be at symbols, but they look kind of like shrimp. At t equals 2. So we know what we're looking for. We're given some x and y coordinates. And we know, if we think back to statics and everything that we've just talked about, we can relate x and y to get us a position vector, which then we can take derivatives of to find velocity and acceleration. Right? So I'm going to go ahead and I'm going to start finding a position vector for this thing. Right? So it could be at any point on this line over here when we're at 2 seconds. Right? We don't know where it is. It's somewhere there. But we can have a position vector that gives us where this is. So that position vector, again, r, is going to be x I hat plus y j hat. And we have no z component here since they didn't give us one. It's happening entirely in this 2D plane, so we won't need to worry about a z component. What we can do instead is just start plugging things in, right? I know my x in terms of t, and I want everything in terms of t, right? I have to take derivatives with respect to time. So I want everything in terms of t's. My position vector is going to be 8t I hat plus, and then I have this y function here of x squared over 10 j hat, which is not ideal, right? I still have an x in there instead of having everything in terms of time. But again, I know that x equals 8t, right? This is something that they gave me, so I can go ahead and just substitute this guy in as well. I'm going to have my vector r is 8t I hat plus 8t in parentheses squared over 10 j hat. So this is looking a lot better, right? This is looking like a really good position vector to tell me where we are in terms of time. So at any given time, I can find that exact xy position vector telling us where we are on that nice little blue line of the weather balloon. But our position isn't something that we really care about right now. right? It didn't ask us to find a position at a given time. We're only interested in that velocity and acceleration. And again, our velocity is going to be a derivative of that position function with respect to time. So we're going to go ahead, say velocity is dr dt, and we're going to take the derivative of that position vector with respect to time. The derivative of my x component here with respect to time, derivative of 8t, is just going to give me 8. 8 for my I hat position. Now I'm actually going to multiply out this 8t squared over 10, so I have something a little bit easier to work with. So that is 64t squared over 10 in my j hat position. And I'm taking the derivative of that. That's my position there. I want to get the velocity. So derivative for this y component is going to be plus, bring that 2 down, so 2 times 64 is 128 times t all over 10 j hat. And so I wanted to find that velocity at 2 seconds. So my velocity at 2 seconds is going to be 8 I hat, and then just plug in 2 for t. 128 times 2 over 10 j hat. Which is great and all, but it didn't really ask for it in vector form. It explicitly said what's the magnitude and direction of that velocity. So if we remember, our magnitude can be given just by taking the square root of the squares of the components. So that velocity magnitude is going to be the square root of the x component, 8 squared, plus the square root of the y component, which is going to be, oh gosh, let's simplify this to 128 over 5. I don't know if I even, nope, I did not punch this into a calculator. I have no idea what this is. 128 over 5 squared. To get a magnitude of velocity of about 26.8, and let's double check our units here. X is in feet, so this is going to be feet per second. That's our magnitude. Now our direction, although we didn't talk about it, our direction really just comes from our trig background, right? The direction being the angle that that velocity is acting. So the angle that that velocity is acting is going to be arctangent of the y component over the x component. And again, that's really a throwback to earlier algebra classes. We did it some in statics, but this is really a throwback to that, where we can plug in arctangent of that 128 over 5 all over 8 into a calculator to see what angle, what direction that velocity is acting in. So in my calculator, I got about 72.6 degrees. 72.6 degrees. So that's our velocity. And then just one more thing to find. We want to find our magnitude and direction of the acceleration at 2 seconds. So we have this handy velocity function, and our velocity, if we take the derivative of that with respect to time, gives us our acceleration, right? Acceleration is dv dt. So I'm going to take the derivative of this guy. I'm going to say, okay, the derivative of 8. 8's a constant, so when we take the derivative with respect to time, we're going to get 0. No more x component because there was a constant velocity in that x component. Plus, then we'll take the derivative of our y component, which is 128t times 10, so the derivative of that is going to be 128 over 10 j hat. So again, this one is even easier to find the magnitude of because it's only acting in one direction. It only acts in the j direction. So if I punch that into a calculator, I'm going to get that the magnitude of that acceleration is, whoops, put that point in the wrong place. Let's fix that. Divide by 10, not by 100. 128 divided by 10 is 12.8 feet per second squared. And then what direction is that acting in? Do I even need to do math to find out? Not really, because it acts entirely in the j direction. It acts entirely in that y component direction, which means it's going to be acting straight upwards, right? No acceleration in the x, only acceleration in the y. So the direction this acceleration is acting in is 90 degrees, just straight up. So let's take a look at another example. So in this example, we have a little airplane, and it says the path of our plane is described by y equals 0.001 x squared meters. If a plane is rising with a constant upward velocity of 10 meters per second, determine the magnitudes of velocity and acceleration of the plane when it reaches an altitude of 100 meters. Oof, these problems, they throw a lot of words and a lot of things at you. It can be really hard to digest. That's why I like to always write out anything important that I'm given, anything that I can pull out of this blurb. So path of the plane is described by y equals 0.001 x squared. That sounds pretty important to me. Sounds like a good relationship to write down. Y is 0.001 x squared. This is our plane is rising with a constant upward velocity. Constant upward velocity. So what that tells us is really two things. One is that the velocity upwards, so in the y direction, in looking at this picture, upwards is our y direction, is going to be a positive 10 meters per second. But it also tells us implicitly that there is no acceleration in the y direction. No acceleration. Acceleration equals 0 in the y direction. And what we want to find is our magnitude of velocity and magnitude of acceleration at an altitude of y equals 100 meters. We're given 100 meters, we're given a velocity, we're given this relationship between y and x. But what we're not given in any of this is anything to do with time. There's no time relationship here whatsoever. So what we're going to have to use instead is that special relationship we have between velocities and dy dx. So we talked about very briefly, we have this special relationship between y dot is dy dx times x dot. Or another way to write it, we have velocity in the y direction is the derivative of the y function with respect to x times velocity in the x direction. If we kind of think about what that means for us and what that can help us find, is that remember we're trying to find magnitude of velocity here. So magnitude of velocity just by its definition is going to be the square root of vx squared times vy squared. So I'm going to need both of those things. Just because we have that constant upward velocity of 10 meters per second doesn't mean there's no velocity in the x direction. We've got to find out what that is. And that relationship between x and y is how we can get there. So from our givens, we know what that y velocity is. We know I can plug in 10 for vy. Now for this dy dx term, all that is the derivative of my y function with respect to x. So the y function we had was 0.001 x squared. So if I take the derivative of that, derivative of y with respect to x is going to be 0.002 x. So I can plug that into this equation as well. 0.002x times Vx. And Vx is what I'm looking for so that I can plug it into my magnitude function over here. But what is this guy? What is this x then? Right? I'm given that I want to find when y is 100, what is our velocity? And I'm given a relationship between y and x. We can actually backtrack and we can go find out what the x value is when y is 100 to plug into this equation here so that we can solve for Vx. And I'm going to erase this, clean this up a little bit. Put my x back in here. So if I have y equals 0.001 x squared, I know that I want y to equal 100. So 100 equals 0.001 x squared. When I divide that over and then take the square root, so divide that over, I get, what is that, like 100,000, square root of 100,000? And plug that into a calculator. I get 316.2 feet. Right, so when this y is 100, I get this x value here, where the plane is of 316.2. And that's the x that I'm going to plug in here. 10 equals 0.002 times 316.2 Vx. Whoops. And now I can do the algebra to solve for Vx, just dividing over these components underneath my 10. So that I can get my velocity in the x direction is 15.8 meters per second. So now I have my Vx, I have my Vy that was given to me in the problem statement up here. I can find the overall magnitude of that velocity. Velocity is the square root of 15.8 squared plus 10 squared. Simple as popping that in the calculator. Calculator gives me 18.7 meters per second. Right, so that velocity, it's not acting just in one direction, it's acting up at this angle here. And did it ask us to find that? No, just the magnitude of velocity. Easy enough. I don't have to do anything else. I can just find this magnitude of velocity. Only other thing it asked me for was the magnitude of acceleration as well. Excellent. So we're halfway done, right? We have our magnitude of our velocity. So now how do we go about finding that magnitude of acceleration? Magnitude of acceleration there. So our acceleration, much like velocity, is going to be the x component of the acceleration squared plus the y component of the acceleration squared. Take the square root of that, that's going to give you your overall magnitude of acceleration. Although in this case we know that we don't have to do this, right? We don't necessarily have to use this equation because ay is 0. There's no acceleration in the y direction, right? It told us there's a constant upward velocity. It tells us there's no acceleration in the y direction. So really the magnitude of acceleration is just whatever the x acceleration is. That's going to be our overall magnitude since our 0 in the y direction cancels it out. But again, we still have no time. We have no really good way to take a derivative of velocity because we don't have velocity in terms of time. We just have a number for the value of velocity at y equals 100. So what we're going to have to do is use another special relationship, kind of like this guy that we talked about. And that's going to be our y double dot, right? Y double prime, the second derivative of y equals d squared y over dx squared times x dot squared plus dy dx times x double dot. And again, this is just the dot notation form, but we can write it in our more conventional, maybe what we're a little bit more comfortable with, where the second derivative of this y with respect to time is just ay. We have the second derivative of our y function with respect to x. Then we have this x dot. Remember, x dot is just the derivative of x with respect to time, so that's velocity in the x direction squared, plus dy dx times our second derivative of x is going to be ax. And this is the guy we're looking for. This right here, this is the puppy we're solving for. So let's take a look at what we have, what we don't have, and how we can solve for this guy. So ay, we said we already had. It was given to us in the problem statement. We just established ay is 0. No acceleration in the x direction, constant velocity there. Then I need to take the second derivative of that y function with respect to x. So my first derivative, did we put that somewhere? Oh, we put it just in the equation. Let's go ahead and write that out. Let's write out, we had dy dx. What was our y? I'm gonna have to write that out again. So if y equals 0.001 x squared, then dy dx is 0.002x. Then the second derivative of that with respect to x is going to be 0.002. Right? No more x component, just 0.002. It's a constant acceleration. So I can plug that into my formula over here. 0.002 times the velocity in my x direction. We calculated that. 15.8 squared plus dy dx. So our dy dx, remember this is at y equals 100. We said at y equals 100, our x is 316.2. That's going to be 316.2 times ax. We can move that over to the other side, and we get a magnitude of acceleration, or magnitude. Our signs, our direction do not matter. Our magnitude of acceleration, when I punch this into the calculator, is 0.79 meters per second squared. 0.79 meters per second squared in the x direction, which is, again, our overall acceleration in this case. And we don't need a direction, but if we did, we know it's entirely in the x direction. So again, these curvilinear motion problems, they're a lot like the rectilinear, where it's just keeping in mind that position, velocity, acceleration, they're all related by being derivatives of each other. You can integrate to get to each other, with some special exceptions that we have these special relationships for these derivatives with respect to time when we have it in position, when we're given a position in our XY coordinate system. And the next few videos, we'll talk about a couple of other coordinate systems that may be more useful for a different problem type.